Directed fuzzers steer execution towards specific vulnerable code regions to verify patches, yet they routinely run for 24 hours without triggering the target crash. The first reason they fail is how they navigate. Directed fuzzers rely on static analysis to compute distance metrics, graphing a route from the entry point to the vulnerable sink. This graph breaks down when the target code uses indirect calls. When C or C++ programs use function pointers or virtual dispatch, static analysis cannot resolve where the call leads. The execution path simply disappears. Take a heap buffer overflow in the web server Nginx. The vulnerable sink function is ngx sendfile r. Because it is reached via function pointers, static analysis draws no edge connecting the harness to the sink. The fuzzer's distance metric reads this missing edge as infinite distance. The fuzzer receives no gradient to guide it. No matter how many millions of times the engine mutates the byte-level input, it cannot steer toward a path it cannot see. The incompleteness of static analysis renders reachable, vulnerable paths completely invisible. The distance-based guidance mechanism is broken before the fuzzer even begins executing. Even when a fuzzer successfully maps the path and reaches the target function, it hits another barrier. Triggering a crash requires satisfying precise input-level conditions. Strict data flow dependencies and formatting checks often sit right in front of the vulnerability. In an OpenJPEG library vulnerability, the crash site inside OPJ J2K decode tile is gated by 6 concurrent tile geometry predicates. The tile grid must begin at the origin, the output window must be perfectly aligned to the codex tile size, and the dimensional variables must match perfectly. A seed that reaches the function looks identical to one that satisfies all 6 predicates from the perspective of a coverage feedback loop. There is zero signal to reward partial progress on structural constraints. Blind byte-level mutation relies on random probability to guess these specific values. A standard 24-hour fuzzing campaign will exhaust its time budget long before it satisfies all 6 variables simultaneously. Blind mutation lacks the semantic reasoning to solve multivariable structural constraints. To bypass these checks, the fuzzing pipeline requires a different intervention entirely. Instead of trying to rebuild a fuzzer's internal scheduling and mutation engines, the most efficient intervention point is the initial seed corpus. This is the design principle behind SeedSmith. It replaces rigid static analysis snapshots with an iterative, agentic large language model workflow that investigates a codebase much like a human security analyst. The process starts with target preparation. SeedSmith parses the C or C++ codebase, extracting functions, global variables, and type definitions into a queryable knowledge base. The system then splits into 2 distinct stages. A heavyweight analysis agent conducts deep code exploration and outputs a structured analysis report. This report is handed to a cheaper, lightweight seed generation agent that synthesizes the actual testing payloads. By separating the expensive reasoning task from the repetitive generation task, the system minimizes computational costs while outputting initial seeds with high semantic quality and structural validity. We can see this reasoning engine at work on a vulnerability in the Poplar PDF library, known as PDF018. Standard static tools like CodeQL completely fail to build a database here. Inside the vulnerable sync function, annotank.draw, a loop iterates over an array. On line 19, there is a fatal null pointer dereference. With no call graph to rely on, the analysis agent interrogates the queryable knowledge base. It issues a context-aware search. Under what exact conditions does an inklist array element become null? The search returns an adjacent function, parse inklist. The agent discovers the array is 0 initialized using memset. Further down, the logic states the array is only populated if an isArray check passes. Non-array elements silently skip assignment, leaving a zeroed null slot intact. Having identified the crash condition, the agent works backward. It queries the codebase again, mapping the execution path up to the harness and confirming it requires a virtual dispatch call to annote.draw. A standard single-shot LLM prompt looks only at the sink. It misses the adjacent memset command, failing to understand how the null condition is created. Iterative, context-aware code search is required to uncover the interprocedural dependencies that trigger deep bugs. Now the system must build the actual input file. Here, large language models encounter a severe limitation. They hallucinate when attempting to output highly structured raw binary bytes directly. To bypass this, SeedSmith restricts the seed generation agent from writing raw bytes. Instead, it instructs the agent to write a programmatic Python script that imports standard format libraries to construct the seed. For Poplar, the agent outputs a script using a standard library to build an ink list array. The script first constructs a perfectly valid set of PDF coordinates. This ensures the file passes the initial format validators, acting as the first line of defense. Then, it injects the necessary trigger. The script appends the raw integer 42 to the end of that valid array. When this generated PDF is processed, the integer 42 successfully bypasses the top-level PDF lexer. But once it hits parse ink list, it trips the isArray check, leaving exactly one null slot in memory for the target loop to dereference. Translating abstract semantic reasoning into byte-perfect constraints requires an intermediate step. Emitting programmatic scripts is the reliable mechanism for producing real-world testing payloads. Because SeedSmith operates entirely as a front-end seed generator, these inputs are completely fuzzer-agnostic. They require zero modifications to downstream fuzzing engines. This graph tracks bugs crashed over time across 4 Magma benchmark fuzzers. Fuzzers equipped with SeedSmith seeds achieve crash time speedups up to 14 times faster than defaults. The SeedSmith plots spike sharply within the first hour, while the baseline climbs gradually over 24 hours. A significant portion of this initial spike consists of one-shot crashes. The LLM-generated seed triggers the vulnerability on its very first execution, before the fuzzer applies a single mutation. When you drop these targeted seeds into a general-purpose fuzzer like AFL++, it actually outperforms dedicated directed fuzzers at exposing specific bugs. Providing semantically rich initial seeds shifts the computational burden. The fuzzer is no longer searching an impossible state space. It is simply performing rapid local refinement. We see the same pattern hold when moving from highly controlled benchmarks to the ARVO dataset, which consists of real-world open-source projects. Looking at bugs triggered over 24 hours on ARVO, SeedSmith exposed 16 previously unreachable crashes. These bugs span 10 projects utilizing diverse formats, from binary headers to compression frames. The language model's pre-training successfully maps to arbitrary constraints that random bytes cannot guess. Currently, language model inference is too slow and expensive to be integrated directly into a fuzzer's microsecond-level mutation execution loop. The value of the model lies in performing heavy semantic deduction before the execution phase begins. By offloading path resolution and formatting constraints to an autonomous agent upfront, the historical bottlenecks of directed fuzzing are removed. Blind exploration becomes targeted exploitation.